nice. I have.
You can use it. It's
I
mine,
can
but you
use
can
it.
use it. Yeah, yeah, sure.
Yeah. So good. So that make it safe. Make it safer.
Okay. Yeah, you're good to go. All right.
Okay.
Okay. Great.
Hello. Okay. Okay, let's get started. So I'm Yuan Yu. I'm a member of the Google Brain team. So mainly working on scalable infrastructures for deep learning. So, my talk today is about distributed control flow in TensorFlow. So first, what is TensorFlow? The TensorFlow is Google's deep learning system. It's a large-scale deep learning system. And the system has been used very widely inside Google, and it has been used for search, for ad, for instance, DeepMind's AlphaGo, and a lot of other things. And it is incredibly useful to us, and so we thought the community will actually love it. So we open sourced it last November. And within 6 months or 7 months, it becomes one of the most popular uh, GitHub project. So so the license for the TensorFlow is very liberal. It's going to be it's actually the Apache 2.0. So what is deep learning? So deep learning effectively is to learn a complicated function from data that maps from one space to another space. For example, and you can have in the space space one, in the first space you have a space of images, and for your space two is a Boolean space, is cat or no cat. So the function is going to tell whether, given an image, whether the image contains a cat or not. So the function itself is represented um, as, a, as a network of neurons and trying to emulate the human brain. So a neuron is effectively a very simple mathematical function that takes some output of some neurons and generate a new value. And that value is going to be used, consumed by some other neurons. So the what is the deep learning? So is, I mean, also for this function, there's a lot of variables, and for some of the models we have like billions of variables. So the job of deep learning is to train those variables so that I give an image and I can tell whether the image contains a cat or not. So one standard way of training those variables is to use gradient descent. So it's just very primitive calculus concept. So therefore, all the functions involved in the neural network are differentiable functions. And then you can actually apply the chain rules to compute the gradients of this function. So why do we care about this whole thing, and why this community should learn something about this? So many of the key challenges we face in TensorFlow are about programming language design and implementation. So here's a few examples. We need to come up with the right abstractions to program those neural networks. And also, because of the computation, the deep learning, the training aspect of it extremely data and also compute intensive. So therefore, we're using all kinds of computing devices. We're using CPUs, we're using GPUs, and also Google actually, and also some other companies, we actually work on custom hardwares. And so the a big problem is, a big question is how to compile computations to run on those devices. Of course, also we want to support distributed and parallel executions on a cluster of this kind of computing devices. Imagine the clusters contains tens of thousands of this kind of computing devices, and how to get all those computing devices, all the CPUs, GPUs, TPUs work together to do some computation. It's at a very large scale. That is the problem we need to solve. And also, there's a lot of program transformations, optimizations, and believe me, it's very, very challenging, and also is very, very relevant to the programming language community. So basically, TensorFlow is a software stack. So it runs on all kinds of devices, CPU, GPU, and the TPU. So TPU is our a Google custom hardware, which is it stands for Tensor Processing Unit. So, and on top of it is a layer that is essentially is execution layer, execution engine. So and on top of the execution engine, so we have a lot of mathematical operators. So we implement all kinds of mathematical operations that is needed for deep learning, and so and those mathematical operations typically have multiple kernels or multiple implementations, and it runs on either CPU, GPU, or TPU. So on top of this, so this is all written in C++. And then we surface different language bindings. And so the Python API is the most popular one because of this is actually the one. So if you talk to the machine learning researchers, and so the language they use is Python. So therefore, we have to surface a Python API. And there's also a C++ API, and also people are working on Java bindings and Go bindings and some other languages. And on top of it is just application user models, and people create a lot of models for translation, for speech, for all kinds of things, image recognition, and also it's part of the ecosystem, and people can use it, and people can play with it. So what is this talk about? So this talk is about one interesting aspect of the system. So that's how to support control flow constructs in TensorFlow. And so so everyone knows, we want to do the conditionals. That means we want to be able to execute part of the program or part of the model and ignore some other part of the model based on some condition. And also we want to do while loops, and we want to provide some higher order functions that allows them to program, allows the people to write program. So why this is hard? So the first problem is we want to support distributed and parallel computation execution. So that means, for instance, in a while loop, the loop body can be actually partitioned onto a set of devices. And so therefore, the computation has to be, each device is going to run its part of the computation, but there is going to be a coordination to collectively decide when the loop is going to terminate and whether there's going to be a next iteration. So, and also we like to have multiple iterations to run in parallel. So effectively, effectively is a data flow model. So we want, if there is no data dependency, the, the multiple iterations, the operations in multiple iterations should be able to run in parallel. And we want to make sure they can actually run in parallel. And so there's another very challenging problem, which is I'm not going to talk about in this talk, is how to do automatic differentiation. That means how to compute gradient for these control flow constructs. So the basic idea is do a lot of program generation. So we take the control flow constructs, we generate a program that automatically generate a program that does the does does the does the gradient computation. And so when we put the two programs together, and that becomes a very large program, and so the entire large program can be actually run in a parallel mode. So that means effectively the system allows you to compute gradient uh, in, a, in a very parallel and distributed way. So why do we need this control flow? And typically, if you look at the literatures of deep learning, so there's a few layers of the neural network and a few layers of neurons, and they stack together. So that is what happened in the past few years. But there are there are some new classes of deep learning models. And so that is very cutting edge and advanced, but in the meantime is showing a lot of promise. So that's a recurrent, for instance, a recurrent network, and there is some kind of a tree and graph network, and also reinforcement learning, which is the kind of things used by the AlphaGo. And so that requires you to have more and more programming constructs. And so in particular, that requires use of control flows. So let's give you a very, very simple example. So that's a recurrent network. So the recurrent network basically is trying to model sequential data. So sequence of data, sequence of things, something. So it could be a sentence, it could be user action, and it could be your history of Google search, and it could be a lot of things. And it's very useful in translation. It's the state-of-the-art translation is actually the inference is using a recurrent neural network. And so the image caption and also videos and audios and all that. So if you look at the code, so a recurrent network is very simple. This is effectively the code pattern. And so we have a sequence. It could be a sentence, or it could be something else. And then we basically keep calling a function. A cell is a complicated mathematical function. And we keep calling the function. That's it. So, but this is something we don't know, for instance, the length of the sequence. So that's why it is a while loop, not a, and so previously people try to solve it by static unrolling. So that means typically you need to have some sort of a max length of the sentence you can handle. And if your sentence end up actually shorter than that, you have to pad the thing. And if it is longer, and you truncate. So, but with control flow, you can express it very, very elegantly. So, so for the rest of the talk, I'm going to give you an overview of the TensorFlow. I'm going to introduce the control flow primitives, and I'll tell you how those control flow constructs I just mentioned is going to be translated into data flow graphs, and also I talked about a little bit about how those things are going to be executed in a distributed fashion. So in TensorFlow, computation is the data flow graph. So nodes are basically operations. And so here is a matrix multiplication, there's a matrix addition, there is some very simple mathematical function, and this is the cross entropy and something like that. So it's just a bunch of mathematical operations. And the edges are essentially the flow of values. The value is effectively just n-dimensional array of some type. typically is a float. So, so the rule of the execution rule for this thing is extremely simple. And for any operations, if the input are ready, available, and this thing can run. So it's completely data dependent. Is a, so that's why it's a data flow execution model. So the way we execute this thing is modular some kind of collocation constraints. The TensorFlow can just partition this graph arbitrarily based on some cost model of where to be where to run the one particular optimally, and so the system is going to decide to try to partition it in some optimal way. So therefore, we can take advantage of all the computing devices. So, so the system is going to do this kind of partition based on some cost model, and obviously one of the problem is if we partition something onto different devices, and so that means the data has to be transferred from one device to another. So the system is going to automatically insert a pair of nodes for any cross device edges, send and receive. And also the receive, in the current implementation, the receive is very proactive. So the receive is going to start is trying to pull the data from the sender. So this send and receive is turned out to be a very nice abstraction that encapsulates all the communication of TensorFlow. And so under the cover, so for instance, if it is two GPUs on the same machine, so we'll do just a GPU to GPU copy. And if it is CPUs on different machines, so we'll do just cross-machine RPC. And if it is GPU on different machines, and we'll do RDMA. So this is all under the cover is implemented, encapsulated, and so most of the people don't see it. So, but a lot of the kind of a graph optimization, and so for instance, to decide the placement of the operations on different devices, assignments, all that things can be done without really understanding all the details about how the things are going to be transferred. So let me just briefly talk about the Python API. So the Python API is divided into two parts. So the first part is a way to construct this kind of data flow graph. We can think about it as a DSL for graph building. So for instance, they declare some W as a variable, which is the variable is essentially is a two-dimensional, it's a matrix with the first dimension is 784, the second dimension is 10. And so here is the variable B is essentially it's just a vector. And so Y is some kind of computation, matrix multiplication, and then do element addition, and then do some kind of another mathematical function called softmax. So this is basically describes the graph, but the execution, there's no execution. So the execution is defined by another thing called session API. So the session API exposes a method called run that can run any of the subgraph created in the graph by the graph building API. So the subgraph is basically defined by the feed and also the fetch. So for instance, I want to feed some value to X, and I want to fetch some value from Y. So the TensorFlow runtime is going to take the feed and the fetch and create this subgraph and optimize it, and then partition it onto different devices and then run it. So the Python API for control flow is just a very, very straightforward extension of that the current Python API. So we introduce something called count, which depending on the predicate, we either, so the F1 and F2 are basically lambdas. When you call it, it's going to create a subgraph. So this is basically says, so this is a subgraph that is going to be executed when the predicate is true, and this is a subgraph that's going to be executed when the predicate is false. And similarly, and we have, for the while loop, we have a lambda that computes the, the condition, the termination condition. And also we have this, the B basically is the body of the while loop. So, so for the rest of the talk, I'm going to talk about how this thing is going to be, the, 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 the two things we are just mentioned here is how this thing is going to be compiled down to data flow graph and executed by TensorFlow. So let's just recap what we know about data flow model. This is data flow model of computation. The computation is expressed as a data flow graph, and nodes are operations, and the edges are data dependencies, and also the basic execution rule is very simple, and an instruction is enabled, an operations node is enabled if all the operands are available. And so the TensorFlow minus the control flow I'm just going to introduce follows this rule. So we borrowed very heavily from the data flow machine research in the 70s or 80s. You know, in the 70s and 80s, there was some very nice piece of work about trying to figure out how to do something different from von Neumann machine. And so they invented something called data flow architectures. There are basically two kinds of architectures. One is static data flow machine, and then there's a dynamic data flow machine. So there's some limitations of the static data flow machine, so therefore we actually adopt the dynamic data flow machine so that trying to give us the maximum possible potential parallelism. So, so the fundamental notion in the dynamic data flow machine is something called execution frame. So that means each while loop is going to have its own execution frame, and the frame can be nested in order to handle nested loops. And so there's also, it also needs to introduce a bunch of a few control flow operators. So that is going to manipulate the execution frames. So this is what I'm going to show you, which is essentially these 5 operators. The 5 operators is, the first one is a switch that allows you to forward the data either to the false branch or the true branch, depending on some predicate. And a merge basically says I have 2 inputs or maybe multiple inputs, and also if there's any input is available, it's going to forward it out. So, and so there's a enter operator that tells you to enter a frame. And so the exit operator that tells you to exit a frame. And also the next iteration tells you to go to the next iteration within that frame. So all those operators are for control flow purposes. And so there's no computation. So they are basically forwarding the data from the input to the output. So now let's look at how the control flow constructs can be compiled to this. So this is how we compile, for instance, the conditional. So the conditional basically is I have two. So so this is my predicate, and so if it is true, I'm going to come here. So the x is going to x comes in because of it's true. The x comes out here, and it's going to do the add one and then merge. And if it is false, and we come here and do this add, and it comes back. So for the merge is going to see only one tensor and one value. And so how about the while loop? The while loop basically is compiled into a form like this. So we enter this is the initial value, and so it's going to enter. And because for the merge, once there's a value available, it's going to forward it. And it goes here, and based on the, and so it goes here and it goes to the predicate. The predicate tells, it goes to the switch, and if it is false, and we exit. If it is true, we do the add, and we comes back. And so the value flows here again. So this is a circular, there's a circular graph. As a graph contains a cycle. So, and how those graphs are going to be executed? So, as we talked about the partitions and also the different devices, and so effectively we have one executor on each device, and so which is effectively manages the execution of the subgraph assigned to that particular device. So the state of the local executor is very simple, and for each node there's a pending count. If the pending count reaches 0, it is enabled, and we can execute it. And also and for each node there is the set of available inputs. When the pending count is 0, all the input must be there. So the execution of a ready node is also very simple, because if it is a node is ready, we perform the computation, we update the pending, and we update the inputs for the successors, and then we execute the new ready nodes. And we can execute it in parallel. We can execute in whatever ways we want to execute. So but with control flow, we have to be a little bit more. So one of the question is, what happened if how to handle the untaken branch of a switch? So we introduce a notion of dead. A node is dead if it is on an untaken branch of a switch. So for that node, what we do is we don't ignore it. We actually propagate, but we skip the computation. So there's no computation on that node, but we do actually propagate this deadness. So this is actually quite useful. It's needed. It's useful for better garbage collection, but it's necessary when we get to the distributed execution. And the propagation is actually quite simple, and any node is dead if one of its input is dead, and except the merge. And the merge is dead only if all its inputs are dead. It's very simple rules. So how do we deal with while loops? So in the case of the while loops, so we need to execute the same node multiple times. So because there is a cycle. So the way we do it is by basically introduce the execution context for each loop iteration. So this execution context is uniquely identified by the frame name and also the iteration counter. So it is exactly in terms of the state of the context, it's exactly the same as before. So we have the pending, we have the inputs. But now, instead of a global thing, but now is for each context, we have this state. So the execution is exactly as before, but only executed in this context. So, so so now let's take a look at a little bit closer look at the control flow context. The control flow context, effectively, as I said, all the primitives are used to manipulate the control flow context. So the enter basically create a new context. So that means we're starting a new while loop. And so the next iteration is going to create a context with counter plus 1. And a context can be garbage collected when the computation is done. So effectively, when a context is done and there is no outstanding operations in that context, and also the context the context for the previous iteration is done. So this is actually highly optimized for parallelism. So that means multiple loops can run in parallel, and multiple iterations of the same loop can also run in parallel. So yeah, so it's all data dependency. So let's now get to the interesting part of this whole thing, is how to do distributed execution of this. So let's just recap what we know about this thing. Is a graph is partitioned into a set of partitions, and each partition runs on a single device and managed by the executor we were talking about. And so there is a execution for the entire computation is done when all the subgraphs are done. So this is actually managed by a master service that gets some kind of signals from all the partitions. If all the partitions are done, and the entire computation is done. So how do we do the distributed execution of conditionals? So the first problem we run into is, suppose I do a partition on the untaken branch. So remember, we talked about the receive. The receive is going to proactively pull the data. If this is on an untaken branch, so if we don't send anything here, so the pull is going to wait forever. So as I said before, so that this is where we need to propagate the Dennis token. So what we do is we actually, even though this part, even for the untaken branches, we actually propagate the Dennis, and so there is actually a token, which is a Boolean token, as sent from the send to the receive. So the receive is going to receive this is that token, and is going to keep propagating this token. And for instance, maybe there's a third device is going to keep propagating. And so how do we deal with the while loop? So a naive partition would say to partition it, to partition the loop body onto a different device. But this is going to be also bad if we do it naively. So the problem is the device B has no context about what exactly the execution context this part of this subgraph is in. So for instance, it doesn't know, it needs to start the next iteration. Also, it doesn't know when to terminate. So the trick is to do graph rewriting. So the basic idea, so it's a very, um, the idea is very simple, but it's turned out to be, the implementation is turned out to be quite tricky. So the basic idea is to add a control as a finite state machine to each partition of the loop. And this is actually as the equivalent transformation of the original graph. So this, we're not changing the semantics of the graph. And then, so the resulting graph is going to be partitioned and executed by TensorFlow. So the beauty about this approach is we can use whatever the local executor we used before. So this is the whole distributed execution is done by this very simple graph rewriting and transformation. So the cost of the communication is also quite good. So that's one tiny message. For every iteration, we need to send one tiny message from the device that is controlling the loop termination to each of the participating devices for the loop. So let's take a look at how it is done. So this is the loop, and now it's on two devices. And what we do is we right after the placement of all the ops to devices, and we go through the graph and introduce or add a little finite state machine that controls the execution of this op, or the part of the op in that each partitions of the participating in the loop computation. So, and then we go through this, and then we do the partition, introducing the send and receive. And now the graph it looks like this. So I'm not going to go to the detail, but so this one actually allows you to execute, and so the two executors, in fact, runs completely independently, communicating a little bit of the termination condition, and right. So, and in somewhat more general way, and so if you have a bunch of send and receive, or there's a lot of cross-device edges, and you basically, there's a bunch of send and receive, is all controlled by this little state machine. And so on device A, and also we also have this little state machine that also controls all the receives. So what happens if there's a nested loops, and we just stack the two little state machines together? So that would actually give you the state machine that controls nested loops. And this whole thing is released as part of the TensorFlow open source, and is widely used both internally and externally by a lot of projects and a lot of people. So that's pretty much is my talk. Yes.
Given that you partition the graph using graph rewriting, I assume it's done statically, right?
It's statically.
So how do you do load balancing, and how do you minimize communication costs?
So this is a little bit of beyond the scope of this talk, but what I can tell you is, for this kind of computation, is there's a lot of repeated computation. So we can learn from the history of the computation that we can generate some very, very accurate cost model. Mm-hmm. And so that is typically used to um, us to to optimize the placement of the assignment of the operations to the devices.
So it's basically an offline profile-guided optimization for the partition.
It's right now it's offline, but you can imagine. So if so this kind of it's a training. So for this kind of training, it's a training loop.
Yeah.
There's a lot of data you need to train. You use a lot of data to train. So you can say, for instance, after a few thousands of steps, and you calculate the cost model, and then doing a better, trying to optimize the placement, and then do it again. So it's not completely offline, and but it's not really, the real time uh, adaptive things
Right.
people
Thank you.
may want to see.
Thank you.
Over
Yes.
here. How do you deal with failure? Is there some kind of fault tolerance built into this?
Well, so it's a very interesting question. Um, so the failure for this kind of system, the failure is handled by checkpoints. Okay. So there are some states, and so we periodical checkpoints the system, and and if something crashes, and we just roll back and start from the previous checkpoint.
Thank you.
Oh,
Could you also use this for other stuff than machine learning?
of course. So this is actually becoming so initially is when the project started. So and the application domain is focused purely mainly on the machine learning, in particular in deep learning. And but once now the system is getting more and more general, we start to introduce, for instance, um, shared variables, and we introduce shared state, and we introduce this also the control flow stuff. So that make it more or less a general purpose programming language in some way. So yes, the answer is yes, and so we are certainly trying to push it more and more towards general purpose applications.
Yeah, sorry. Connecting to this, so the user has only consumes this API to set variables and the steps or the transformations on the variables, but you don't have control on the actual formation of the graph, right?
You do have control,
Ah,
right?
so my question will be, do you have an intermediate form in which the user can see how the graph look like, and do you have a
Yeah, so
specification?
there's a graph visualizer, so that allows you to visualize the graph, and but there's it's a little bit more complicated because of the graph. There's many stages of the graph, and it's going to be transformed many times as optimizing compiler does. The code is becoming more and more obscured. So the same thing is true here. So the graph actually end up executing is quite different from the graph you initially constructed. For instance, if we do constant elimination, or we do some kind of a common sub-expression elimination, and so the graph being executed at an executor can be quite different from the graph you construct.
But is there a public API to control this graph as well from the user
No,
perspective?
there's is mainly is a graph visualizer, but there's no API that allows you uh, to there's no, what I should say, there's no GUI.
So can you speak to the limitations? Can you speak to the limitations, problems and issues that you have encountered?
So the limitation. Uh, so that's a very good question. So I mean, I haven't really thought about much about the limitation. So if I want to talk about some limitation is, so uh, I would there is a so as I mentioned, this is so this thing is started as some somewhat narrow scope, and then it's been generalized. So as part of doing this, and I think the programming API needs some work. So, and the programming API is not, so there's a few things which is, for instance, the semantics of this API is not very well defined. And also um, the, uh, the, the use of this API, if you only do deep neural, programming deep neural network, is turned out to be quite is quite adequate. But if you want to do some more general purpose programming, so it's so this is actually is a very good question to the programming language community, is to come up with the right abstraction to program not only the neural network, and also the, the execution engine. We provide this execution engine that allows you to run something at very large scale, and using all kinds of computing devices, and with all the support for control flow and other things. And so the interesting question is, what exactly we can, the programming interface or the programming abstraction on top of it. And so we don't have, we are actively thinking about these kind of things, but it's nowhere near the, we get some good handle. We haven't really got a good handle on this. Yes?
So I'm a bit curious about the predicates in particular, so how they're built up and where they're executed. For example, you had an example where if x is less than y.
Yeah. So you're talking about the predicate here? So let me.
Yes.
Yeah.
Yeah, sure.
Yeah.
I'm curious where that's evaluated and how that computation is built up and distributed. So you can actually.
Yeah, the predicate can be distributed too, so it can be partitioned.
So then are the constructs for building up the conditionals then limited to things that can be expressed in the graph as well, or can they be kind of any arbitrary computation?
It's arbitrary computation that is composed by the operations.
Got it. Okay.
We defined.
So things like less than, greater than are already built into the API.
The less than, greater than is built in, and so
to TensorFlow specifically, not necessarily into the Python.
It's not Python. So
okay.
There's we're talking about the TensorFlow operations. Yeah, if you end up using the Python operations, that means you end up having a round trip from the server to the client. So which is exactly the thing we try to avoid.
Thank you.
Okay. Any questions? Oh, there's one more.
Yeah, so it's just looking at the while loop, for example, it seems like using the word while loop doesn't really match what it's actually doing. Like in the end, when it's executing possibly parallel and possibly over several machines, it doesn't really resemble a while loop anymore as you would think about it. So I was wondering if you'd thought about like what kind of language you would use to describe these kind of distributed and parallel operations that doesn't really match what we intuitively think of as.
So the way I'm inclined to think about this is this is your instruction set for your machine or processor, right? So it could be a while loop. The while loop can be compiled into something like this kind of data flow graph, and for instance, some other higher order operators like fold or map or parallel map and also scan and also can be compiled into this. So and so the instruction set is reasonably general, but we so what exactly the programming construct we want to surface to the user is wide open. Okay. Uh, so the Spark. So Spark starts as a batch processing system, and they started to add something about streaming, and uh, and I think for the kind of applications we were talking about, so this is a this is I would say is a more scalable and also high performance way of doing computation. So and uh, so there is actually some work going on and uh, trying to integrate TensorFlow with Spark. And but you know, so so the way, for instance, Spark doing streaming is quite different from the way we do streaming. So with a while loop, and also something I haven't mentioned is and also in the TensorFlow we have a distributed queue implementation. The combination of a while loop and the queue gives you effectively a streaming way of doing computation. So, but that's something we haven't really explored a lot because we haven't really found any compelling use cases for this. But that's actually is the direction we are actively exploring. Okay.
Thank the speaker.
The job of deep learning is to train those variables so that I given an image and I can tell whether the image contains a cat or not. So one standard way of training those variables is to use gradient descent. So it's just very, very primitive calculus concept. So therefore, all the functions involved in the neural network are differentiable functions. And then you can actually apply the chain rules to compute the gradients of this function. So why do we care about these whole things, and why this community should learn something about this? So many of the key challenges we face in TensorFlow are about programming language design and implementation. So here's a few examples. We need to come up with the right abstractions to program those neural networks. And also, because of the computation, in the space one, in the first space, you have a space of images. And for your space two is a Boolean space, is cat or no cat. So the function is going to tell whether, given an image, whether the image contains a cat or not. So the function itself is represented um, as a network of neurons, and trying to emulate the human brain. So a neuron is effectively a very simple mathematical function that takes some output of some neurons and generate a new value. And that value is going to be used, consumed by some other neurons. So what is the deep learning? So I mean, also for this function, there's a lot of variables. And for some of the models we have, we have like billions of variables. So the deep learning, the training aspect of it is extremely data and also compute intensive. So therefore, we're using all kinds of computing devices. We're using CPUs, we're using GPUs, and also Google actually, and also some other companies, we actually work on custom hardwares. And so a big problem is, the big question is how to compile computations to run on those devices. Of course, also we want to support distributed and parallel executions on a cluster of this kind of computing devices. Imagine the clusters contains tens of thousands of this kind of computing devices, and how to get all those computing devices, all the CPUs, GPUs, TPUs work together to do some computation. It's at a very large scale. That is the problem we need to solve. And also, there's a lot of program transformations, optimizations, and believe me, it's TensorFlow. The TensorFlow is Google's deep learning system. It's a large-scale deep learning system. And the system has been used very widely inside Google, and it has been used for search, for ad, for instance, DeepMind's AlphaGo, and a lot of other things. And it is incredibly useful to us, and so we thought the community will actually love it. So we open sourced it last November. And within 6 months or 7 months, it becomes one of the most popular GitHub project. So the license for the TensorFlow is very liberal. It's going to be it's actually the Apache 2.0. So what is deep learning? So deep learning effectively is to learn a complicated function from data that maps from one space to another space. For example, and you can have in the space, in the it would be nice I have.
You can use it. It's mine,
can
but
use
you can
it.
use it. Yeah.
Yeah, so good. So that make it safe. Make it safer.
Okay. Yeah. You're good to go. All right.
Okay.
Okay. Okay.
Hello. Okay. Okay, let's get started. So I'm Yuan Yu. I'm a member of the Google Brain team. So mainly working on scalable infrastructures for deep learning. So my talk today is about distributed control flow in TensorFlow. So first, what is TensorFlow?